A man drops a rock into a well and hears the sounds of the splash 2.4 seconds later after the release. If the speed of sound is 336 meters per second, how deep is the surface of the water? Question 2. If the travel time is ignored, what percent error is introduced in the calculated depth? Okay. In this problem, it's just a free fall problem with speed of sound. So the rock falls, hits the water. I will call that time T naught. And then it takes time for sound to travel from the surface of the water to the top of the well. And I will call that time delta T. And that delta T is going to be the depth of the well divided, the depth of the well divided by the speed of sound. And then we are going to combine the equations and calculate this. It's very easy to do the calculation numerically using the Inspire calculator, but it's a bit complicated to do it by hand. Okay, this is the rock that is being thrown. Go here, splash, and then you have sound going up. I'm not considering how tall the person is or anything like that. It's going to be from this age. I will put the 0 over here. So this is age, and that's what is being asked. So this times from going from here to the water is T naught. That is not given. And this time of sound going from here to here, I call it delta T. And that delta T is distance over the speed of sound, so H over Bs. Bs is the speed of sound, and T naught is the time to go from here to here. Okay, what is T? He hears the sound at this time. So this T is given, this is 2.4 seconds. This is the one that is given. So, using the kinematic equation, y equals y naught plus b naught t minus 1/2 gt squared, dropped, so initial velocity is 0. The initial position is h, and the final is 0, because I put the 0 over here where the water is. And you know what this is? This is just h equals 1/2, and this is T naught. That's the important thing. This is T naught, is the time to go from here to here. T naught squared. You saw for T naught over here, so T naught is the time that is given minus delta T, or T minus h over the speed of sound. So you put it over here, and it's 1/2 g T that is given h over bs. This is a quadratic equation in h. This is a quadratic equation in h, and if you use the Inspire calculator and do and solve, just put the equation. H 1/2 9.8 2.4 minus h over 336 squared comma h. You get the answer. Right away. So as you can see, the height is 26.4. I mean, the depth is, this is the depth. The depth is 26.4 meters. Okay, suppose that you don't consider the speed of sound, you don't consider this term over here, then the height is just 1/2 g t squared, and this is, I would call it off, because this, the overestimation is going to be deeper than what actually is, and is 28.2 meters. What is the percent error? That's the second question. This is question A. First one is h of minus h over h times 100. So it's 28.2 minus 26.4 over 26.4 times 100, and the percent error is 6.8%. So you get a overestimation of the depth of about 7% if you don't consider the speed of sound. How long does it take sound to go from the splash to the person's ears? Again, I'm not considering that the person is probably about 1.8 meters above the edge over here. I'm not considering how tall the person is. It's not given, and this is the answer. So the actual depth is 26.4, and if you don't consider the speed of sound, you get 28.2, which is 7% off. Now we show you how to do this analytical without using ENSOLVE, without solving this question numerically. It's a quadratic equation in H, and that's what we are going to do next. But if you are interested in just the answer and you are allowed to use the calculator numerical features, that is it. Okay, we are going to take the problem from here. The height is 1/2 g t minus h over the speed of sound squared, and this is a quadratic function in h, so we are going to try to have an analytical equation for the height, and then we substitute the numbers and we can find h by just doing arithmetic operation and a square root. Okay, I'm going to put 2h over g, and I'm going to square this, t squared minus 2th over bs plus h squared over bs squared. I will multiply now by bs, so I get 2 bs squared over g times h, t squared times bs squared minus 2t bs, because the other one cancel here, times h plus h squared. Now I will move everything to one side, so I get h squared. This is negative, and this term, when it's moved to the other side, is also negative. So we take it common factor, and is 2bs squared over g plus 2t_bs, and this is h plus t squared bs squared. Okay, this is my quadratic equation in h. So a is 1, b is negative, and this huge parenthesis, and c is t squared times bs squared. So these are my two solutions, just using the quadratic equation. I need to put this square. We'll leave it like that for now. Minus 4a, that is 1 times c. And then everything is divided by 2 times 1. I'm going to go ahead. I can cancel these 2 and over here as well. The square root of 4 is 2, so it cancels that too, so I don't have a denominator. And I have bs squared over g plus t bs. Put a parenthesis over here. Again, this 2 that was also here is being a square, and then you can be taken out. So that 2 over here is also simplified over here because it's 2 squared and 2 squared and 4 over here. So it's the same term. I just need to square this term. So bs to the 4 over g squared plus 2 bs cubed t over g, that's 2 times each other, plus t squared bs squared. Over here I got minus t squared bs squared. As you can see, the reason I squared this term over here is because this cancel. So let me bring down what is left. And now I could take bs bs squared over g as a common factor. So I need to have g squared over here, so I multiply g squared times g, and I need to get bs to the 4th, so I divide by bs and put to the 4th over here, and now this parenthesis stays the same, and I get bs to the square over g. Anytime I have a square root, I like to have like 1 plus something. And I have over here 2 gt gt has units of velocity, divided by bs, that is velocity. So this is dimensionless. And over here I have bs squared over g plus dbs. What is bs squared over g? It has units of distance, right? So meters square second square over meters per second square. So b squared over g has units of meters. That's why I wanted to. So let's take bsg as a common factor out of everything. So I need bs squared over here. So I need to divide by bs. And I need g over here. So I need to multiply by g. And now we take bs squared over g 1 plus, and over here I get gt over bs, and I took this one out, it's plus minus square root 1 plus 2 gt over bs. And this is my equation for the high. I have two solutions. I need to see now how to, if it's the plus or if it is the minus. Okay, gt over bs is small, 0.07. Bs square divided by 9.8 is big. So this over here is 1.07, and this is plus minus, and then you have a square root of something plus 2 times 0.07. So square root of 1.1 plus 2 times 0.07, that is square root of 1.14. And that gives a number that is extremely close to this. So if you use the plus sign is about 2. This bracket over here is about 2. And this number is huge. 11,000 meters. So both solutions, the plus and the minus, are positive, but you know that it has to be less than 1/2 gt squared. And this is going to be twice. If you use the plus, this is 1 and this is close to 1. So twice this is 20,000 meters. It makes no sense because this is, you need to be less than 28 meters. So it has to be the negative solution. So h is bs squared over g minus over bs. So this is the height. So again, what is in the brackets is a small number. And when you multiply by this big number, you get the 26 point something, which is less than 28. And this is how you do it without using the numerical features that your calculator has. So this is very interesting because this doesn't, you expect this to be something like 1/2 gt squared. You get this speed of sound everywhere in the equation. So we are going to Taylor expand this square root function over here, because remember GTBS is small, so we consider that x is small, so we could Taylor span around x equals 0 and transform this equation into something that make more sense, like 1/2 gt t something t squared. So this first derivative over here is square root is 1/2, so the 1/2 go to the front, and 1/2 minus 1 is negative 1/2, so it's at the denominator. But when you evaluate this at 0, this 2, derivative of 2x is 2, so this cancels, so the derivative of 0 is just 1. So, and the first derivative is just this. That's the first derivative. So the second one at 0. So this is negative 1/2 that goes to the front. The derivative of 1 plus 2x is 2. So these two over here cancel again. And 1/2 minus 1 is negative 3/2. That's why it's at the denominator. So this is the second derivative. This is 3/2. But when you evaluate at 0, you get negative 1. You get negative 1. That's it. We are going to stop there. So 1 plus 2x is the function at 0, that is 1, plus x minus 1/2 x squared. So h is bs squared over g, 1 plus, remember, x is gt over bs. It's a small number, 0.07, so I can do a Taylor expansion, minus, and now I put the Taylor expansion over here, 1 plus x minus 1/2 x squared, etc. You can see this term cancel, and negative times negative is plus, and I got 1 bs over g squared times 1/2 x squared. What x is this? So I got bs squared over g, 1/2 g squared t squared over bs squared. And now that makes sense, plus other terms that I didn't do. So this cancel, and h is in this approximation is what to expect, 1/2 gt squared, which it doesn't look that this equation is 1/2 gt squared, because you have this speed of sound term everywhere. Now let's do the first correction, and this is interesting. If you want the first correction, the first term that has the speed of sound, you need to Taylor expand this function up to the third derivative, and that's what I'm going to do next. The Taylor expansion up to the second term does not give us the speed of sound term. So if we need to get the third derivative, the cubic term over here, in order to have the first speed of sound term, and then it's going to make sense because the high is going to be this minus a term. So this is the second order Taylor expansion. So we need to get the third term. So the third derivative is negative 3/2 minus 1 is negative 5/2. Again, these two cancel. And the factorial of 3 is 1 over 3 times 2 times 1. So it's 1/6. So we get here plus, no, negative. We get, let me do it over here. We get 1 plus x minus 1/2 squared. Now negative again is 1/6 times 3. You get 1/2 because the factorial is 1 over 6, but you're multiplying by negative 3, so you get 1/2 x cubed. And it has to be negative because it has to be less than this. And look, I got a negative. All right, so let's continue now the Taylor expansion of this function here. So it's going to be h equals b squared over g, and then 1 plus x minus, and now I have 1 plus x minus 1/2 x squared minus 1/2 x cubed, and other terms. Again, this cancel. And I get bs squared over g 1/2 x squared and negative. It's supposed to be positive, so negative and positive is negative. This term is supposed to be negative. Let me see if I find a mistake. Okay, this second derivative over here is negative because this is negative 1/2. It goes to the front. And yes, these two, the derivative of 2x is 2 and cancel the half, but you still have it negative. That's why I put it over here, negative. And x equals 0, you get negative 1. So this negative and this negative becomes positive. That's why this term over here is plus. minus negative is negative, and it's supposed to be like that because you know that it has to be less than 1/2 gt squared. So again, let's take x 1/2 bs squared over g x squared 1 minus x, and this is the first correction. Remember, x is gt over bs, so I get 1/2 bs squared over g, and now I got g squared t squared bs squared like I did before. This cancel. It's independent of the speed of sound. I mean, this term one cancel, and this is 1 minus gt over bs and other terms. So h is, and this is how I like it, the equation, because physically it makes sense. You know, it's going to be 1/2 gt squared and something less than that. And this is the third order approximation. And that's how it makes sense. Physically speaking, you have the speed of sound as a factor out to 1/2 gt squared. So compare this with this. It's very hard to understand how this is an approximation of 1/2 gt squared. But if you Taylor expand this function over here, as I did over here, on the third order approximation is where you get it. The second order is 1 gt squared, and the first order is 1 gt squared. You need to have to take up to the third derivative to see the speed of sound. And what is this? You know that this is, so if this was the off calculations that I did, is just 1/2 gt squared, and you do off minus h over h, you get this term over here that is this 0.07 gt over bs is 0.07, so you get 7%, because this is the factor. So this is the equation for the high up to the third order. This is the equation for the high exact, just using the quadratic equation. And it was very hard to see that this equation is an approximation of 1/2 gt squared. To see that this is indeed, to see that this equation, the first order term in this equation is 1/2 gt squared, you have to do the Taylor expansion of 1 plus 2x. Remember, x is gt over bs, is unitless and is small. Because it's small, no, it was 0.07. Because it's small, you can Taylor expand this function around 0. This is the Taylor function when x is small. And we get an equation that makes sense physically, because we have the 1/2 gt squared, that's the free fall, no speed of sound consideration, minus this factor over here that you know is a small number because the speed of sound is huge in comparison to gt. gt is way smaller than 336. And that's all. This is very interesting problem to practice Taylor expansion and approximating functions.